Okay, TEST-11C, this is class 9 science, force and laws of motion. Okay, so 11C, these questions. So let's just start with the first one. Activity 11.5. So you write it down on page 166. Open your textbook to page 166. I'll read the question for us. An object of mass 20 kg is dropped from a height of 4 meters. Fill in the blanks in the following table by computing the potential energy and kinetic energy in each case. So we will do like this. Draw along with me the table first. So we have here a table we need to know. So here, so this is the one. And serial number, let us start with the first one, serial number. 1, 2, 3 will go like that. Then height at which object is located. So we may as well make it a little bit longer than this. So here, height at which object is located. Write it down along with me. Let's denote this one by the letter H, and in meters, the height even in the unit meters. So let's say this is the first one. So we draw a line. Then the second column is we're going to calculate the potential energy. So potential energy, let us say, and the formula also, just keep it here. We know potential energy is, we're going to use this mgh, and it is going to be using the unit joules, let us say. The next kinetic energy, here we know formula we're going to use is half mv square. The very two famous equations for potential and kinetic energy respectively. The unit that we will use is joules to find out. Okay, and then the last row and the last column is we're going to add up these two potential energy, whatever we got in each case, and kinetic energy in joules we're going to do, let us say. So we have space here, down next here. The first one, 5 serial numbers are there. So 1, 2, 3, 4, and 5. So that will be enough. So the first one, let's start with serial number 1. Okay, and then we'll go one by one. We'll solve here. So before we start serial number 1, as we read the question just a moment ago, we found mass is 20 kg, m here mass 20 kg. Then we are going to use g, which is, I think they didn't give, but we're going to use, they gave for simplifying just below the table the calculations. Take the value of g as 10 meters per second square. So question has given us 10 meters per second square, and then in that case we're going to use a. Okay, we're going to use acceleration also. So a is the same as g when the object is dropped. So it is traveling in the same direction from drop from top to bottom, means g is always positive, a is always positive, so plus 10 meters per second square. If we throw the object up, then a would have been minus 10, and we can give the reason for this. Since here downward fall, downward, the object is clearly in the question saying, you can see the object 20 kg is dropped, so from downward fall, that's why plus. This thrown upwards, we know it is going to be minus 10 meters per second square. Okay, so this is the value. Let's start with serial number 1. Solving the serial number 1. When the object is at a height of, serial number 1, when the object is at a height of, you look into your question, 4 meters above the ground. So height object is located at 4 meters 4 meters above the ground before it is dropped, that means. So in such case here, H1. Now let us draw a figure to help us here. Maybe we can draw it here. Space is a little bit cramped for, but anyway, okay, here let us try. So let us say this is the object that is dropped from top A, here B, C, D and E, here ground level. So this is the ground level. We may write it down, ground level, this one. So initially the object was at height of 4 meters. So this height here, H, from here to here, when before it was dropped and before the object was moving, H1 equal to 4 meters. So this is the one we're taking. So when it is like this stationary, first case H1 is equal to 4 meters. We will write here. We'll do slowly, okay? So we get it, height above ground. Height above the ground when the object, just before the object was dropped. That means the object was not moving. Then V1, since the object was yet to be released, it will be 0 meter per second. This is the velocity, because the object is not yet dropped, so there is no velocity. Then therefore with this we can calculate the first potential energy, EP1, let us put, is equal to mass of the object is going to be said, G is same here, H1. So mass is 20 kg, G is 10 meter per second square, and H1 is 4 meters, as we can see. So here 4 2s are 8 and 2 0 kg here, and here meter per second square into 1 meter is here. Follow this carefully, because from the next sum I think we can go directly. So here 800, we know, we've been doing this. This is the best unit of force, which is Newton, right? We can write in short as Newton. Kg meter per second square, Newton is same. And Newton meter can be written in SI unit of, this is the SI unit, but in the short form as joule. So here the first potential energy, when the height, it was at the height of 4 meters above ground before being dropped, potential energy was 800 joules. Like that, this sum is saying, filling the blanks by calculating from serial number 1 when object is at 4 meters, at 3 meters, like that we're going to go. Then EK1, so let us write here, EK1. EK1 is going to be half into M is 20 kg, and V square is, V1 is, okay, once we write the formula, half mv1 square when the object is at the height of 4 meters, it is not yet moving, into 20 kg into v1 is here, as we can see, 0 meter per second, whole thing if you want, square. So 0 into 0 0, you can neglect that, and so you're going to get here 210. So 10 into 0 again 0, so everything is going to turn out 0 because of this 0 joules finally. So when it was at the height of 4 meters before being dropped, before moving, since the object is not moving, kinetic energy will be 0, because kinetic energy is energy possessed by a moving body only, so it has not yet moved. Okay, so the total is 800 plus 0, EP plus EK, total is 800 joule, proving that the law of conservation of energy is being proved here, that nothing is lost, right? Let's go to serial number 2 now. At serial number 2 here, number 2. Now question says go to textbook at 3 meters. So when object has reached 3 meters, it has moved some distance. So it has fallen from here to here. This much distance it has moved. Let us say S1. From here, this point, see, B. From A to B is 1 meter, okay, like that. So it has dropped 1 meter. So the H2 will be here this H2. So let us write here H2 is equal to at 3 meter above the ground. So when it has traveled from 4 meter to 3 meter above ground, H2 in the serial number 2 will be, so it is now at a lesser height from the ground, 3 meter. And now we may just avoid this for timing, then write that one down, serial number 2. Now, so therefore we can write potential energy in the second case will be mg will be same, and h is height 2. Now the height is changed from 4 to 3, so mass is 20 kg, 10 meter per second square in the 3 meter. So that is 3 2s are 600 kg meter per second square up to here, and into meter, which is 600 Newton meter, which is 600 joules. So we've explained the serial one, so I didn't explain Newton meter and all. So I hope that's fine. So in the second case, the potential energy is 600 joules. That's how we're going to have to go about doing it. Now for kinetic energy. So now to calculate the kinetic energy, we need to take the distance traveled. This is the height above the ground, H2, which is 3 meter, which is here 3 meter. We know that, but we have to take, okay, we need not write also, okay, write if you want. Now you see here, when it is at 3 meter above ground, the object has fallen from A to B, means travel this much AB distance. So this is the S1. So this is the S2, sorry, let us just put it as S2. Okay, S2. Corresponding S1 is also fine, but 2. The distance traveled in serial number 2 is, when it is at 4 and fallen to 3, means it has this travel this much, and this much is, we know S2 is here. See, this one is full here, from here to here is H1 minus H2. This here, this one minus H2, 4 minus 3, then it has traveled 1 meter. So this is 4 meter minus 3 meter. So the distance moved is 1 meter. We need this for kinetic energy. We're going to do it in a slightly different way, okay, from serial number 2. So we have S2 now. V2 is the velocity in the second case. So with how much velocity it has fallen from A to B, we don't know. So just put serial number 2 velocities, we don't know. Now we know in the motion equation, since twice AS is equal to V square minus U square, okay? V square minus U square. So in this case, we're going to have to put acceleration is going to be same throughout, but S we have put 2, so here S2. V we have put, so V2 square, and U is going to be same throughout. So let us calculate this V2 square. So here V2 square don't move, then here 2AS, right, 2AS. Since we are done with this potential energy, I think we can drop out this part, and you can write here. Okay, so that implies 2AS, fine, then shift this one here, minus U square this side, 2AS2, sorry, then plus U square is equal to here V2 square. We want to find V2 square, so 2 into A is 10 meter per second square into S2, just now here 1 meter, plus U, though, since the object, read the question, says drop from the top, means initial velocity U is always 0 in every case, so 0 meter per second whole thing square. So this part can be neglected, is equal to V2 square. So V2 square we're going to get equal to, here this, I think this is going to be okay, so 2 tens are 20, meter into meter, meter square. Again you shift it up, then second to the power plus 2 will become minus 2. So let us just keep it like the V2 square we got. V2 square value 20 meter square per second square. So let us now find the kinetic energy in the second case. It's quite easy, I think. So E K2 will be half mv2 this time because second case square. Half into m is 20 kg into v2 square here. Just now we got it. V2 square is 20 meter square per second square. Same thing. Then 2 tens are 20. So you're going to get here 2 into 10, 200 kg. Now meter square means double meter is there. Take 1 meter per second square and shift this one at the back meter. Then we're going to get here 200. This kg meter per second square we know by now is Newton, and here meter, so this is 200 joules. So kinetic energy in serial number 2 is 200 joules, proving that the law of conservation of energy is true. Again, 600 plus 200, EP plus EK is coming out same. We're trying to show also that this total is not going to change, even though potential is changing from 800 to 600 and kinetic from 0 to suddenly jumping 200. The total is still same, meaning no energy is lost. So law of conservation of energy is being proven right here, right? So finish serial number 2. Let us go to serial number 3. In serial number 3, the object would have fallen from here to here, serial number 2. Now to C means serial number 3. So it came here, right here. Let's see. So that is the point. So this is H3, which is equal to 2 meter. So serial number 3 is, the object is at 2 meter height. So in that case, it has moved from here, from here to here. So the distance traveled would be from here to here, now here, from here to here. So here, from here to here it has fallen. So this is the S3, right? S3. So let's do slowly. Serial number 3, S3. Let's do the potential energy first. So similarly for serial number 3, look at your text here. Yes, serial number 3, H3. The height above the ground is now 2 meter. This is the height above the ground level. So we can just calculate that, I think, directly, the potential energy. EP3 therefore is formula for potential energy is mgh, so H3 this time. So this will be, m is the same object, so 20 mass same. G is 10 meter per second square into H3 is 2 meter. So it's a simple case of 2 2s are 4 and then double 0 here. Kg meter per second square into meter. So this is 400 Newton meter, which is 400 joules. So potential energy in the third case is 400 joules. So we're realizing that as the object falls from top and comes nearer and nearer the ground level, potential energy is decreasing and kinetic energy is increasing 0 to 200, and we will see more increase here. So let us go to the next one, that is kinetic energy calculation. So this S3, that is the distance traveled from this point 1, 2, 3, so for serial number 3. At serial number 3, it is height above 2 meter means, ground means, it has traveled this distance, which is this. So that is S3. S3 will be equal to, common sense only, from here to here, we know H1. H1 minus this portion you see here, H3 here. If you do here, okay, a little bit up. So from here, H3. So here, 4 meter, as you can see, minus H3 here. H3, this one, is 2 meter, which is H3. So H3 will be H1 minus H3 will be 4 minus 2. So that is 2. So 4 meter above ground minus 2 meter, that much, 2 meter above ground. So 4 minus this 2 is this much. The distance dropped, the distance traveled, which is equal to 2 meter is the distance traveled in the third case. We need this, right? Now velocity v, we need velocity, so v3 is question mark. How fast it's moving, we don't know. Velocity in the third serial number. So we've applied the same formula twice. As, this time S3 is equal to V3 square minus U3 square, the motion equation. So likewise, like before we have done, V3 square will be twice AS plus U square. Bringing this side, minus will become plus. So 2 into A is 10 meter per second square into S3 is here just now. 2 meter plus 0 meter per second, because the object is dropped, so U is going to be 0 in all the cases, so square is equal to V3 square. So V3 square finally will be 2 tens are 20, 2 twos are 4, so 40. 4 tens are 40. Meter into meter, meter square, second to the power minus 2. So V3 square we got. So with this we can calculate the kinetic energy in the third case, which we can write as EK3 will be half m V3 square. Okay. So here I'm just going to write half into 20 kg into V3. Just now we got here V3 square is 40 meter square per second square. So this 2 can cancel this 10, then 14 to 10 is 400 kg meter per second square, and 1 meter, double meter is here, meter square, 1 meter can go back here, kg meter 1 second square, and then 1 meter at the back, so that we can adjust it to show this is kg meter per second square is, we can write, adjust and show it as Newton and meter, which is basically 400 joules. So here we got in the third case 400 joules. Again, the total 400 plus 400 is not changing in the last column. That's what we are trying to show, right? So serial number 4. Let's go to serial number 4 slowly. So serial number 4 is now here. First it was here H1 equal to 4 meter. Then second it was here H2 equal to 3. Third it was here C, H3 equal to 2 meter. Now the object has come here D. So somewhere here, so here this is H4. H4 is equal to, given in the question itself, 1 meter above ground. Look there in your textbook, 1 meter above ground. So when it is 1 meter above ground, the distance traveled is from here top to here is S3. Like this it should go, okay? So here, from here to here traveled, from here to here dropped. Just 1 meter above ground means it has traveled from here to here, which is S4. Okay, so S4. Anyway, so here H4, height above ground, in this case is clearly 1 meter, the height of the object above the ground. So we can calculate the potential energy. EP4 in this case is mgh4, right? So slowly, mass of the object is not going to change. It's the same object, 20 kg into 10 meter per second square into 1 meter here, h4. 2 tenths are 200 kg meter per second square up to here, and here 1 meter. So that is 200. This portion we know is Newton and meter here, so 200 joules. So kinetic energy has increased in the fourth place. When it is 1 meter above ground, it is decreasing. So it's as it is nearing the ground, sorry, the potential energy is decreasing. Kinetic energy is increasing. See here, 0, 200, 400 now. So we write here 200. Then let us calculate the kinetic energy like we've done for the previous 3 cases. Just go, so we need S4. So the distance traveled in the fourth case will be, common sense you see here, from here to here S4 will be, this height from here to here we know is H1 minus from here to here 1 meter, this 1 meter cut. total is 4 minus this. When the object is 1 meter above ground means minus h4 will give you this one, which is the distance traveled, s4 in the fourth case. So that is h1 4 meter minus 1 meter, which is equal to 3 meter is the distance traveled. Okay, distance traveled in the fourth case. Okay, now V4, the velocity in the fourth case, serial number 4, we don't know yet, but we know this formula. A is not going to change. S in this case is S4, V4 square minus U square, using the equation for motion. 2a is equal to V square minus U square. So let's just put here V square, don't move, V4 square, sorry, and then 2as4, this part is okay, then shift this one, the minus will become plus U square. So this is 2 into A is 10 meter per second square into S4. As we can see here, S4 is 3 meter, the distance traveled. So plus U is always 0 meter per second, because the object is dropped, means U is like the square is equal to V4 square. So V4 square is going to be this side. Okay, I think we don't need to go one more step, that is enough. See here now, 2 3s are 6, so 60 0 here, meter into meter, meter square, and second to the power minus 2. So V4 square we got. So we can easily calculate the kinetic energy, because we needed V. We already arranged in V4 square. So EK4 will be half into MV4 square. So this is half into M is 20 kg into V4 square. Already arranged for us. V4 square is 60 meter square per second square. So we can cancel this if you want. 2 times are 20. So X is there. So 120, 600 kg. This meter double, you can make it meter square, and meter, only one you take per second square, and take the meter back here. Then you're going to get 600. This portion is we know Newton meter here. So this is going to be 600 joules. Okay, 600 joules there, kinetic energy. So here we fill it up. Again, we see that the total is 200 plus 600 is the last column here. Total of potential and kinetic energy is remaining constant, means unchanged. So the solving we're doing is also correct, most probably. The last serial number 5. When the object reached the ground immediately, what is the potential and kinetic energy? So we have to calculate the potential and kinetic energy at different points in this question. So here, let's not write out this one. So this one. And finally, when the object is reaching the ground, here on the ground level, that is H5 is 0 meter. Ground reaching means there is no distance above ground. H5 is simply 0 meter, the height above the ground. Above the ground. So easily we can calculate the potential energy, EP5 mg H5. M is 20 kg, G is 10 meter per second square, H5 is 0 meter. So very easy to calculate this one, I think. When 0 is there in any factor, 0 into 0, everything will become 0 joules. So when the object has reached the ground, there is no more. When it is just above the ground, the question is written just above the ground. So you also write just above the ground means it's already touching the ground, so there is no distance above ground, so energy is coming out 0 joules. We have to calculate the kinetic energy finally. So let us do that. So S5 is the distance traveled. So when it is S5, it will be from here 4 meter height, it touched the ground means it has traveled 4 meter. Right, so that is, you can also show it as H1 minus H5. H1 minus, yeah, H5 is just above the ground. Okay, so you can just write here directly also S5 by common sense also. When it is touching the ground, the distance traveled is, initially it was at 4 meter height, and touching ground means it has traveled 4 meters. So straight away we can write 4 meter. Okay, distance traveled, sorry, distance traveled. Then V5 is the question mark velocity in the fifth case. So we apply the formula twice. S5 is equal to V5 square, V square minus U square, so U square. So V square, don't move that, V5 square, sorry. Then 2AS 5 here, AS5, a bit bottom. This one shifted, become plus U square. So slowly you do 2 into A is 10 meter per second square into S5 is here, as you can see, 4 meter plus U is always 0, so 0 meter per second. Whole thing square is equal to V5 square. So V5 square will be 2 4s are 8. So I'm going to write 80, 0 is here, meter into meter, meter square, and here second to the power minus 2. So V5 square is 80 meters square per second square. So we can finally calculate the kinetic energy for the fifth case by the formula EK5 equal to half mv5 square. So half into m is, we know, 20 kg, and v5 square is here 80 meters square second to the power minus 2. So 2 tens are 20, 8 into 3, 18 into 10 is 800 kg meter per second square, and 1 meter at the back because there is double meter here, as you can see. So 1 meter here and another one here. So we can write here finally here 800, this part is Newton, you know, kg meter per second square into meter, so that will be 800 Newton meter can be written as short as joules, as we know. So here the kinetic energy is the highest when it just touched the ground. 0 plus 800 again is 800. So we see that the last column, potential energy plus kinetic energy, is remaining same throughout the fall, proving that the law of conservation of energy is true. So that's how we solve it. Okay, we've done this is quite a little bit long, not hard. We'll do the next in the next tree in the next class. I hope you've understood.